Now for the theoretical background. Let us go back to section 3 of this notebook, and this time we're going to start all the way from the very foundation. This is how we started everything, from a segment of a parametric curve and appropriate axis of rotation, and rotate this curve appropriately, and what we get a 3D surface, kind of like this, a surface of revolution. You can play with this using your mouse, and then appropriate viewpoint will give you something like this, clearly showing you that this is a surface of revolution. You see circles, right? Okay. Oh, what happened? I didn't want this to be so big. Okay, maybe I have to rerun this program. Okay. Now, how do I express the surface area of this? One good strategy is to decompose it into several pieces, kind of like this. And here, I put some arbitrary gaps in between each band. There are 5 of them, by the way. But in reality, you shouldn't be able to see anything. So the picture you saw before and this one should be exactly the same. I just added some gaps to see those bands better. Now, if you add up the area of these 5 bands, then of course you'll have to get the original surface area back. Even if I change the number of bands, nothing significant takes place as a matter of fact, except that we have more gaps which I put arbitrarily, which you shouldn't be able to see in reality. Okay, that was fun. And what we're going to do now is to approximate the area of surface area of each individual band using frustums. What am I talking about here? Let's go back to these bands and then let's pay particular attention to the boundary edges of these obtained by smooth surface. Because of those curved surface, we see those curved boundary edges of all these individual bands. But if we replace all these by frustums, which has straight boundary edges, then we're going to get an approximation which we'll be able to calculate. That's the strategy. Okay, let's move on to the specific technique of these. And the very first step is to begin with polygonal approximation, just like the way we handle the arc length. Let's expand this picture and then explain this again. Well, the blue curve is the original 2D curve, the parametric curve, and in order to find out its arc length, what do? We put appropriate partition and then draw line segments which are represented in red in this case. And then each individual length, the length of each individual line segments, which are represented in red here, can be calculated using the Pythagorean formula, because delta SI is a hypotenuse of the right triangle given by horizontal and vertical edges. So what do we have? We have this kind of computation, and dividing by delta Ti and multiplying those again, we end up with a Riemann sum. So upon taking the limit of this Riemann sum here, we're going to get the arc length formula, and that was the strategy we took for 2D case, arc length formula. We do something very similar here, but we do that in 3D version. Let's look at 2D and 3D pictures at the same time, kind of like this. Now this 3D picture you see down here is obtained by rotating that polygonal approximation, in other words those red line segments, with respect to the same axis of rotation. Consequently, we ended up with a surface of revolution with those straight bands or frustums actually, which approximate the one we started off with. This one versus that one. Well, let's look at those side by side, or one after another, kind of like this. Approximation, isn't it? Is it good approximation? No, not really, because we took only 5 bands. But if we increase the number, you're gonna get probably better approximation. I don't know, Mathematica can handle about 15, but well, it did handle, alright. Okay. Too many gaps here because of those computational glitch, I think. No, not computational glitch, actually. I set those gaps myself, except that the gap seems to be a bit too large this time. Anyway, each of these bands are supposed to be frustums, as a matter of fact. They should have straight edges compared with these, which are inherently curved. But if we have n equals to 15, it's difficult to see that, so bad approximation in this case does actually a better job explaining what kind of approximation we are up to. So here it is. The surface area can be approximated by the sum of these areas of frustums, which we call delta AIs. And if we can express this delta AIs as function of t's, then we are going to get Riemann sum. That's our strategy. So from this point on, let's concentrate upon how to get an area of one individual frustum. Okay, it's obtained kind of like this. What is a frustum, by the way? It's a part of the cone. We begin with a cone like this and take away the pointy part, and what's left is called a frustum. And another way to see it is that it's a surface of revolution given by a straight line segment. So this kind of frustum, you can regard this frustum as the one obtained by each individual line segment in this 2D picture, for example, in this polygonal approximation. This part, or left hand side part like this. Okay, it's a bit flipped around to the other side, but well, you can see those. Alright, now one more observation, please. Let's go back to the 2D picture. The length of each individual line segment was delta Si. I have to show you a bit more. Delta Si, which can be calculated like this. That was a backbone of this arc length formula, wasn't it? Now that's the same as in this 3D picture. The line segment obtained by the side of this frustum, which is represented by those black dotted line segments in this picture. Let's flip it. No, I like the previous picture better, excuse me. The black line segment on top, that corresponds to delta Si. And also, some further observation, the radius of the top circle here in this frustum is the radius of this rotation here in this picture, and the circumference will be 2 pi r1, 2 pi r I minus 1 in general, and then the bottom one will be 2 pi ri, and then radius will be just ri. As a matter of fact, okay, everything is summarized here. Now if we cut this frustum along this top edge and then unfold it into 2D figure, you're gonna get this kind of blue figure. And we have those dotted line segments here because that part corresponds to the pointy part of the cone which we took away early on. And everything is labeled here. Delta SI, that corresponds to the top edge, which even originally came from the polygonal line segment or the red line segment we saw before. And then this bottom circle has to match this arc, and the top circle has to match this arc. Okay, let's arrange it like this. Top circle 2 pi I minus 1, and then bottom circle 2 pi ri, kind of like this. And let's find out how to express the area of this frustum, which means the area of this strip over here in 2D picture. So how do we do that? Well, it can be expressed as a difference between area of the large sector, blue, minus the area of smaller sector, red, over here. And then, well, for simplicity, I'm using R1 and R2 instead of Ri minus 1 and Ri here. And then delta S is what we want as a side. And then that's artificially I named the radii as S1 and S2, as you can see. S1, the red one, the smaller radius, and S2, the larger one. So the area of the large sector is by area formula 1/2 theta times S2 squared. And then the smaller one is 1/2 theta times S1 squared. All you have to do now is to manipulate this thing a little bit. How do we do that? Here's the manipulation. S2 squared minus S1 squared can be factored because this is square minus square, kind of like this. S1 plus S2 times S2 minus S1. That difference is significant because S2 minus S1, that is delta S we want. And how about this S1 plus S2? Well, let S be the average of S1 and S2. So S1 plus S2 over 2 will be replaced by just S, which is expressed in purple here. And then theta now, that can be represented according to radian measure as arc length over the radius. What is the arc length? Let R be the average of R1 and R2, red and blue. Then 2 pi R is gonna be this average that corresponds to S. So 2 pi R over S is angle theta. Okay, hard part is all over. All the geometry and all the labeling, everything is all done now, and I really miss face-to-face meeting with all the pictures that I can actually draw with my hand with a lot more labeling. This is the best I can do for now. After some simplification, we have finally this expression, 2 pi r times delta x. That is the area of the individual frustums, each of those. So if I add them up, then finally I'm gonna get this expression, 2 pi ri times delta si. And what is delta si? We have seen those before. That's the arc length elements, so we can use Pythagorean identity, and then we can express like this, the way we did for arc length. And those ri, those are radii, radius of rotation. That's also a function of t. Consequently, we end up with this surface area formula upon taking the limit of this Riemann sum. Complicated, wasn't it? If you understood, great. If you didn't, you can still use this formula.